Whenever you are ready, can you tell me about what you built and how it works?
Yeah, so our objective was to do something cool, and so we wanted to do an accelerator project of some sort of algorithm, and we wanted to be able to visualize what we were working with. And so we saw some inspiration from some of the algorithms that you discussed in class. And upon further investigation, we thought that the diamond square algorithm would be really cool to generate different landscapes, and then we could use different coloring schemes to show different biomes. So that was the overall goal and idea of what we wanted to accomplish.
And then kind of how we implemented it is the project is kind of Verilog based. So in our Verilog program, we have a giant kind of solver that the way that this algorithm works, it's a fractal landscape model, and then based on the depth of the landscape, the solver computes all of the points in the landscape and stores them into M10K memory. And it does this through a sequence of kind of fractal weighted averages with added randomness. And then after they're all stored into memory, we read them in sequence and display them on the VGA SD RAM. So.
Yeah, and then just for some customization, so part of the algorithm includes generating these random values, and then in the Verilog that we have like shift registers for that. So then we wanted to be able to have the user change that. So then on the C side, we have like a simple command line interface where you can change certain parameters such as those random values, but also because, well, in order to calculate the fractal landscape, we need to start with some values for like quarters, which is how the algorithm works. So we also allow the customization of that. And then the final one is we wanted to be able to display different types of landscapes, so like different sorts of biomes or environments. So like we have like a volcanic one, like a swamp one, many different things like that. So that's also, yeah, we'll see them very soon.
Yeah, so for the demonstration portion, the first thing we'll do is we'll run our command line interface. So this kind of starts with a seed for the first map, which is our default one. We reset the FPGA. This is our kind of swamp map.
Cool.
It's it's a lot of bodies of water. It's supposed to be kind of a very at sea level type of orientation. And the way that it works, since our fractal depth is pretty large, we're displaying 257 pixels, and it's kind of using almost all of our M10K blocks. It's kind of a lot of different examples of the same biome. Obviously, if we were looking naturally, it'd probably be maybe one subsection of this blown up. We're duplicating it in many different places because of the fractal depth that we're using. And then so if I wanted to change the settings for this map specifically, I can add a new random seed, and then if I reset it, the map will kind of switch around.
Cool.
So kind of that basically, the randomness is calculated at the every weighted point average, and as we get to lower fractal depths, the randomness is less affecting of the overall calculation. And then I could add some new corners. If I want to change them, I'll just add a value, make them all 0. And this will kind of basically function as sort of the random seed, sort of. Kind of doesn't change it very much because the seed is still the same. But basically, the corner values influence the first middle value, which influences the beginning of kind of the fractal kind of snowballing effect. And then finally, we'll change the color settings. So I'll change it. This is our swamp map. I'll change it to our desert map here. And if I reset it again, I'll get the desert map, which looks like looks like a piece of matzah.
Yeah.
It does.
Yeah. So maybe there's like landscapes exist in the food as well. That's like a question. And this one kind of similarly, between the landscapes, we're changing both the set of colors and also the thresholding for the altitude of where the different colors appear. So that kind of gives it, otherwise it would be the same kind of landscape geometry, which is with different colors, but this kind of switches up a little bit. So we can do, I'll skip the seed for this one. And then check another map. We'll do our Arctic map. This one is kind of, we think looks like a dust map, sort of like a dust under your bed kind of mothball type thing. But we also think it's like a bunch of amoebas under a microscope, sort of.
Vaguely lunar too.
Vaguely lunar, yeah. And this is supposed to be like a kind of Antarctica thing. And then I think, I mean, some of the colors are hard to see. Even like the more like, these are going to be a high altitude section. You can see there's like more coloration in there if you're looking at it topographically.
Yeah. The last two are the coolest.
The last two ones are the coolest. Yeah, we differ on which one is the best. But this one is our Mustafar, for the Star Wars people out there, map. This is kind of our like lava type map, which I think is pretty cool. We think it looks really nice. And we like the kind of the coloration. Kind of there's like lava lakes in them. And then the higher altitude areas are kind of like mountainous, kind of gray and dark regions. And then I'll just do another random seed for this because one is a little bit cooler. It's kind of interesting.
That's
We like to
really
look for like specific kind of geometric formations of something we can see is recognizable in each one, which was pretty fun. So, and the last one, which is my favorite, is the islands map, which we think looks like kind of the Philippines. That one we think is cool because it's like a. If you look at one of the land masses, you'll see that in the water regions that are more shallow, you can see like a lighter watercolor.
Yes.
As if you're looking kind of at a map, you would see kind of that from like a plane or something
Like
of
a
that nature.
reef or something.
Right.
Yeah.
Yeah. Which you think exemplifies actually what the terrain would look like realistically pretty well.
That's really cool.
On the land, there's also a little bit of greenery.
Yeah, we have
It's
kind of,
very, like,
Very small greenery.
Yeah.
yeah.
Small
For the more established land patches, they kind of go beyond just the coastline and stuff like that.
Are all the corners set at the same altitude?
So, they're randomly assigned.
Okay, can you raise one way up?
I can't. Yeah. Seed. We'll do 255. We'll raise one of the corners to the max value. I don't think it'll affect the algorithm very much, but I think that raised. I believe that corner. The way that it works is usually though, the value of a corner will I can only slightly influence the values right next to it, because they're calculated at a much later fractal depth. It'll more likely influence the value in the very middle. But if the other ones are mostly 0 and the top one is only 255, it'll end up being like roughly the same. We haven't felt that changing the corner values influence the positioning as much as changing the seed.
Huh.
So we felt that we're dealing with 8-bit altitude here, and the seed values actually, the random values calculated on each averages, they start out being accounting for overflow and underflow up to 255, and each fractal depth that we go down, we decrease the number of bits that the randomness affects the addition by. So I feel like that was more indicative of the changing, but yeah.
What's the fractal dimension more or less? Is this
The dimension, so let me think about it. So this is a 257 pixel map, which means that we are doing 8 different fractal stages. Yeah.
So each one is a bit smaller than the one before.
Yeah.
Okay.
So that's going down, it's like a slope of -1.
Right, and we think that if we made it a little bit smoother, we would have kind of more prominent land masses. So for example, like we could see like landmass like this, something like that would be blown up much larger, because the nearby terrain would be closer to it, meaning it's more like a zoomed in higher resolution map. So yeah, we experimented with zooming in a different lens, but we didn't think it was good enough to demo. So.
Very nice. And is the VGA being manipulated by the FPGA?
Yeah.
Okay.
So originally, actually, we worked on writing directly to the VGA SRAM. We found that to synthesize maps as big as this, that was running out of MTK memory. So we have a bus master writing to the SDRAM on the VGA. It basically, this is actually only using one solver, but it's still quick enough that we haven't felt there's any kind of performance loss. But it fills the MTK blocks, and then the bus master writes all of them to the VGA in order, sharpening by the columns.
Very nice. Thank you.